All right, welcome everybody. I'm Doug Davis, track host. Obviously, Jan is going to be talking about authentication and security for gRPC. Just one housekeeping thing. Please try to remember at the end of the session, rate it through the app itself so the organizers can know whether you liked it, disliked it, whatever. And with that, I'll hand it over to Jan to give us a talk. Thank you.
Okay, so hello everyone. Thank you. Hello everyone, so you already know, my name is Jan. I'm software engineer at Google. I'm also a member of the gRPC team, and I'm proud owner of the gRPC implementation in the C# language. So today's talk is called Authentication and Security in gRPC Microservices. So what's it gonna be about? First, I'll show you some of the basic building blocks for securing gRPC services, and I'll show you how they fit together. Sorry. Okay. Okay, sorry. I'll show you some of the basic building blocks and how they fit together. I'll start with the very basics that might be familiar to many of you, but I'll later get into a little bit more advanced scenarios, because one thing is knowing the concepts and the other one is securing a real-life application. Part of this presentation is also going to be a demo. And in the demo, I'll focus on running microservices in a Kubernetes cluster. The expectations from you as the audience is that you already know what gRPC is. You maybe run some RPCs, you ran the Hello World example, you know some of the basics, just how to get around with gRPC. This talk might feel a little bit basic to some, but that's kind of working as intended, because security and authentication, these are topics where the stakes are usually pretty high. So we should really understand what we're doing, and that's the only way to avoid mistakes. So first, I wanted to review some of the key ideas behind the gRPC security design. I think it's very useful for understanding the how and why. So I already kind of said that building authentication and security is a lot about avoiding mistakes. So when building gRPC, we wanted to build it on top of standard and proven technologies. And then from user's perspective, when you're actually writing the code, we made the insecure option in the API explicit. So that means when you're browsing the code, you can immediately see maybe this channel is set as an insecure channel. So maybe it's not such a good idea to send some sensitive data over it. gRPC is also multi-language, and so despite every language being different, we try to provide a unified experience and kind of similar feel across multiple languages, while still making it feel natural in every given language. So the approach we took, so gRPC is extremely versatile and universal, and it can run on multiple platforms. It can run in different environments. We didn't want to take the approach of basically imposing on you what's the specific authentication solution that you should use. But rather than that, we provided kind of a general framework to do auth and security, and to do it in a way that fits your use case. And then the specific technical solution would be the actual auth method that you choose, the code patterns that appear in your code, the choice of the third-party tools that you use. And the ecosystem around gRPC is already pretty big, and it's always growing. So there's definitely options out there. We're also trying to provide best practices and recommendations. The community helps us a lot with that, and there's already a lot of blog posts around gRPC authentication. So I talked about using standard and proven technologies, and it's pretty well known that gRPC is actually just a thin framing layer on top of the HTTP2 protocol version 2. And while HTTP2 is still relatively new, HTTP as a protocol has been around for a long time. So vast amount of knowledge and experience has been accumulated around authenticating HTTP traffic. And the nice thing is, with gRPC, this knowledge is not lost. So most of what you know about securing HTTP traffic still applies for gRPC. So if you have a solution that already works for HTTP traffic that you're familiar with, chances are that's going to work well with gRPC too. So using it won't feel like reinventing the wheel, but maybe more like reapplying common knowledge in a little bit of a new context. And I have a little table here which shows the basic concepts. I'm not sure if, okay, laser pointer probably cannot be seen. So on the left side, there's the HTTP do concept. When you're doing connection level security, so basically encrypted connections with HTTP, that corresponds to using so-called secure channels in gRPC. And whenever you're using request headers for authentication, that's going to correspond to something that's called initial metadata. And just as with request headers, the RPC metadata is actually multi-purpose, so it can be used for auth, but it can be used for other things too. So I kind of already started, but here's the 10,000 feet view of what exists in the world of gRPC authentication. So the first option is you can authenticate individual remote calls. And the way it works is you add a secret token in your calls metadata. And this token allows the other side to verify that you are who you claim to be and possibly to verify some other claims. And to be able to send the secret token over the wire, you obviously need an encrypted medium to protect the token from being stolen. Which brings us to the other authentication method, which is channel level. This means you basically, when you start your communication, you establish an encrypted connection with the peer, and one or both sides authenticate their peer during the initial handshake, and after that, that channel is known to be trusted, and you know that the data is coming from the other side, is from who you expect it to be. The standard way to achieve this is through transport layer security. For gRPC, there are other ways to, there are other transports besides the TLS, but it's a little bit out of scope for this talk. gRPC is also extensible, so it's possible to add new transports, but that's kind of a big investment and it requires a lot of effort, so it's definitely not recommended for 99% of the users. The last way you can do authentication is so-called transparent. And that basically means that you just take the heavy lifting of authentication and you delegate it to some other component in your system. And it can be, for example, an intelligent proxy. That's actually a nice way to decouple your business logic and the security layer itself. And it comes handy especially when building microservices, because with microservices, you're going to have multiple smaller components. And in those components, you probably want to focus on business logic more than on the authentication itself. And then you basically just want to add some layer on top of it that's gonna magically add the authentication and security capabilities. So let's take a closer look at the per call authentication with tokens. So in this context, when I talk about tokens, I have the bearer tokens in mind. So the name bearer comes from the HTTP bearer authentication scheme. And what it means is basically, when you're sending the bearer token, what you're saying is basically give access to some resource to bearer of this specific token that I'm sending around. The tokens come in many kinds. They usually look like cryptic strings. They're usually base 64 or some other encoding. But the ones you'll see the most commonly is OAuth2 and JOT tokens. The main difference between those is that OAuth2 is an opaque token. It's usually emitted by a third party. So you reach out to some other party, you provide some credentials, you get the OAuth2 token in exchange, you send it along with your RPC calls, and then on the server side, once that token is received, you reach out to the third party again to actually verify that that token is actually valid and allows access to given resource. The JSON Web Token, also called JWT, is different in the sense that it is self-contained, and it has three parts. One of them is header, which is not really important right now. The other part is the actual token that contains some data that it's claiming about the owner of the token, and the last part is signature. So JWT tokens are self-contained in the sense that when you receive the JWT token, you can just verify the cryptographic signature of that token, and you know if it's valid or not. Because I'm a gRPC maintainer, I've been following some of the public forums and user questions a lot. So it also turned out that some of the people actually think that when talking about tokens, like sending a password over in the metadata is a good idea, and it qualifies as a token. So please don't do that. It's not such a good idea. You can actually, with the same amount of work, you can actually come up with an authentication scheme that's much safer. So for example, using the JWT tokens, and you're not gonna be sending your own passwords around. Another interesting thing to note is that it seems that when I'm sending an authentication token along with my RPC call, I'm basically going to be sending the data over and over, and especially for the JWT tokens that can be sizable. That's going to be a performance overhead. But it's actually, it turns out not to be a problem, because the HTTP2 implements something that's called HPEG, and it's a scheme for compression of the headers. So when you're sending the same authentication token over and over with calls, HPEG is actually going to compress that away, and you're just going to be sending like a reference to your compression table. Okay, over to securing channels. So the concept of a channel exists in all gRPC implementations. For simplicity, the gRPC connections are just HTTP2 connections, and there are actually two main kinds of gRPC secure channels. So one allows the client to verify that it's talking to the right server, and the other method is where both sides mutually authenticate each other, that they know that the counterpart is who it claims to be. Note that there's no variant where none of the parties authenticates each other, because that's basically useless in practice. So if you're establishing a secure channel, you're probably want to be sending some confidential data, and unless you know who the other side is, there's no point of doing that. So the way it works with TLS, which is the transport layer security, and it's the same idea as with HTTP2 connections, is that the client has certificate authority roots, and the server has a certificate and a private key, and then using the certificate authority, you can verify, the client during the initial handshake can verify that it's talking to the right server. And mutual TLS is kind of a similar idea, but the server also has the certificate authority, and the client has a certificate on its own and a private key. So basically they can verify that the certificate authority has signed the certificate of the other side, and then it's basically genuine. Okay, so mutual TLS is great and very secure if done right, but unfortunately it requires certificates to work. So, and the certificates, they are easy to generate when you're coming up with tests, when you're writing your prototypes. But it becomes much more challenging when running a real application in production. And the reality is that your MTLS secure authentication scheme is only going to be as secure as your key management practices. So if you rely on your private keys and for authentication, and then the keys leak, you're basically done. So one of the practices that are recommended is, for example, the certificate rotation. So even in the case when the attacker gets access to your private keys and the certificates, they can only use it for a limited amount of time. And if you're managing your certificates yourself and you're trying to do things like certificate rotation and do it like every day, it's very easy to mismanage, and then you're basically opening up yourself for security risks. So ideally, we would want a solution that can do mutual TLS, but takes away the pain of and risks associated with cert management. And the good news is such solution exists. There's actually multiple solutions, but one of them is using a service mesh that's called Istio. Can I just, how many people know about Istio? Okay, beautiful. So I don't have to explain. So Istio is an example of the transparent authentication that I talked about before, where authentication can be added to your application basically as a drop-in feature without making any code changes. So before explaining how the Istio authentication works, it's worth mentioning a few useful primitives that are provided by Kubernetes itself as building blocks for Istio authentication. And these primitives can be actually used in simpler applications separately as well. So whenever you're working with authentication, there's necessarily going to be some secret that one of the parties needs to have in order to prove to the other side that it's genuine. And Kubernetes secrets are a super useful concept that allows storing these secrets and distributing them to your deployments. And the way it works is after storing the secret, whenever you create a Kubernetes service, you specify it should have access to a given secret, and then Kubernetes transparently mounts that secret to your container. Kubernetes service accounts are useful for, they're basically a secure way to represent identities in your Kubernetes cluster. So with Istio and Istio authentication, two main components come into play. One of them is Pilot, and that's basically the component that knows about your services in your cluster. And from the Kubernetes service accounts, it can establish identities of those services. And Citadel is kind of the key and certificate management heavy lifting part. So that one actually manages and rotates the TLS certificates. And then the last piece of the puzzle are the Envoy proxies that are deployed as sidecar proxies along with your services. And these Envoy proxies obtain the certificates and private keys in form of a Kubernetes secret, and they establish the mutual TLS authentication transparently between services in your cluster. Okay, so I'm actually going to have 4 little examples, and it's going to take me a minute to set up. So first example is going to be just connecting securely with TLS. The other one is going to be using a JOT token. Then we will set up a mutual TLS, but with manually provided certificates. And then the last one is going to be the service mesh with Istio, and Istio doing the mutual TLS authentication for us. Okay, so what I have here is basically an example Kubernetes cluster. Nothing is currently running there. We can make sure that's actually the case. So it's just a regular Kubernetes cluster. So what I'll have is a client that is very simple, and the only thing it does, it creates a channel, and it passes so-called channel credentials that's going to be configured based on the scenario that we want to run. From that channel, we create a client for a greeter service that only has one method, and we are going to keep invoking that single method, until the end of the time. So I'm going to show you. So this is the method that's creating the credentials. In the first example, the mutual TLS is going to be not used. So the only thing we basically do is create the SSL credentials, and we pass in the certificate authority, which is going to be used to verify that we're talking to the right server. And besides that, I have a server that's also very simple. So for the, and you can see the implementation of the server is basically just start the server on a port, provide some kind of credentials, and they're going to be different based on each case in the example. And then for the case where we're not going to be using mutual TLS yet, so just a regular TLS, we're going to be providing the server-side certificate and the corresponding private key. So I can now go ahead and deploy Okay, so I just deployed the TLS version of my server, and I'm also gonna deploy the corresponding client. Okay, and now I need to wait a little bit, but I'll show you. So if these services have already started, so you can see that, we've already been able to contact the server, and so this time we're connecting with TLS. The other example is going to be using the JSON Web Token authentication, and as I said before, for that we actually need the secure channel already. So we're still going to be using the TLS secure channel, but we're also on top of it going to be providing a JSON Web Token. So in my simple example, I'm basically, so besides providing the channel credentials, that's at this point only contains the certificate authority, I'm also going to be adding so-called call credentials. And my auth interceptor is going to be adding a initial metadata entry with the key authorization, and then add the bearer token, which is going to be a JOT that I just generated. And in my example, generating the JOT is pretty simple, but you can see that I'm generating a JOT that has expiry. It has a subject, which is me, and it has audience, and it's intended for the Hello World service. And then on the server side, the server just verifies that all these claims match up. Okay, so I'm creating the client, and as soon as it starts, I should be able to get some responses from the server. Okay, and you can see it's basically the same example, but this time we've actually been able to authenticate as the subject of the JOT token with the service, and the service has verified that the JOT token was actually intended for it. Okay, so that's JOT. The next example is going to be using mutual TLS. And this time we'll need to replace the server because right now the current server doesn't have the certificate authority specified, and it's not verifying that that the connected client is the one that's allowed to connect. So I'm basically just going to replace the existing server with the one that uses MTLS. And what this is gonna do with the server is besides the certificate and the private key, it's also going to specify the certificate authority that should be used to verify the client. On the client side, I'll need to provide, besides the certificate authority that I already provided, I'll need to provide the client-side certificate, which is now going to be verified, and the corresponding private key. So as now when I actually replace the server with the one that requires mutual TLS, the old servers, the old clients actually stop working because they know then they can no longer establish the connection with the server. But if I actually, okay, I haven't started the client yet. So if I actually start the MTLS client, you'll see that that one can, okay, so I started the client and you can see that it's been able to authenticate via mutual TLS. Okay, and the last example that I have is doing mutual TLS with Istio. So the way it's going to work is that I specify a server that actually uses no security at all, but I'm also going to use the istio-ctl command to inject the sidecar proxy, and the sidecar proxy will take care of actually establishing the mutual TLS connection. So I'm going to replace the existing server. Okay. Okay, and then I can also deploy the client. Okay. So this time when asking for the logs, I'll need to, there's actually two containers running in my pod. One of them is the actual greeter client, and the other one is the Istio sidecar, is the Envoy sidecar proxy. So you can see that the client can connect to the server, and the way to verify that it's actually authenticated via mutual TLS. Okay. So not okay. I'm actually not sure what happened with this one, but all the examples are available on GitHub. So I invite you to check them out and see how it's done. And I also don't have that much time left, so so I'm gonna thank you for attention. And before you ask any questions, I just wanted to give a shout out to Vishal's talk tomorrow. It's going to be about gRPC load balancing. It's in the C2 room. If you want to chat with me personally, or chat with other people that know about gRPC, please meet me at the CNCF answer bar on Thursday. It's in the sponsor showcase hall, or you can just chat to me, in the hallway after this presentation. And down there is a link to the demo repository that's public, and it has all the examples and all the commands that you need to run to try it for yourself.
We have 5 minutes for questions.
Okay.
Anybody have any questions? All right. Okay. I guess that's thank you guys very much. Don't forget, please rate the talk when you're through the app when you're done. And thank you very much. Thank you, Jan.